In today's lecture, we are going to start a new packet of notes dealing with nodal analysis and mesh analysis, which is sometimes also called loop analysis. If you think back to the past few lectures, we've been focusing on solving circuits by simplifying them first, combining resistors in series and parallel, combining sources, maybe doing source transformations using voltage division, current division. All these different techniques, the idea was the same. Take the circuit, find a way to simplify it to make it easier to solve for what you are ultimately looking for. In this packet of notes, it's a totally different approach to solving circuits. In nodal and mesh analysis, we are going to solve the circuit without simplifying anything. Instead, we're going to come up with very specific algorithms for finding whatever we're looking for. In the book, you want to read sections 4.1 through 4.8. We're going to start by talking about the basics of nodal and mesh analysis and defining what we mean by single node pair and single loop circuits, because single node pair circuits and single loop circuits are simplified versions of nodal and mesh analysis that'll make it easier to understand those more complicated methods that we're going to see after that. In nodal analysis, we're going to break it down into two types: circuits with grounded voltage sources and circuits with floating voltage sources. Grounded voltage sources are covered in sections 4.2 and 4.3 of the book, and in section 4.4 is where we have floating voltage sources. We will then talk about mesh analysis. In mesh analysis, we have circuits where current sources would be on the perimeter, and we have circuits where current sources are what we call interior, and we'll discuss what we mean by that. But sections 4.5 and 4.6 cover perimeter current source circuits, and section 4.7 covers circuits where current sources would be in the interior. Finally, in section 4.8, we will compare nodal and mesh analysis and see whether one is better than another in different situations. So little preliminaries first here. As I mentioned, nodal and mesh analysis are alternatives to circuit simplification. They're both going to be systematic approaches to solving circuits. In nodal analysis, the variables we're going to use are node voltages. Specifically, we're talking about absolute voltages here with respect to ground. Even though the variables are voltages, the equations we're going to use in nodal analysis are Kirchhoff's current law equations. So voltage variables by Kirchhoff's current law. And we're going to come up with a system of linear equations that we're going to solve to find all the node voltages. Once we know all those node voltages, you could find any current or any power you need by doing simple relationships. We're going to see that nodal analysis is an extension of single node pair analysis, which we will look at first. Mesh analysis is the dual of nodal analysis. In mesh analysis, currents are going to be the variables, but the equations we're going to use are Kirchhoff's voltage law equations. So once again, it's weird, current variables, but Kirchhoff's voltage law. Like nodal analysis, we're going to have a system of equations we're going to solve to find all of the mesh currents in the circuit. Once we have those mesh currents, any other variable we're looking for, any voltage, any power, etc., we can find relatively easily. Finally, we're going to see that mesh analysis is an extension of single loop analysis. So what we want to do now is talk about these two simplified circuits, single node pair circuits and single loop circuits, because these are the precursors to nodal analysis and mesh analysis, respectively. So a single node pair circuit is a circuit where every single element is in parallel, so it only has two nodes. It has a node on the bottom and a node on the top. If you only have two nodes, that means that there's only a single voltage in the entire circuit, a single voltage variable V, and that is the difference between those two nodes. In a single loop circuit, every element is in series, and so there is only a single current throughout the whole circuit. So once again, single node pair circuits only have a single voltage, single loop circuits only have a single current. So let's see how we would solve both a single node pair circuit and then a single loop circuit, and then we'll extend these ideas to nodal analysis and mesh analysis. So a single node pair circuit is one where all the components are in parallel. For example, you might have a resistor, an independent current source, maybe another resistor, maybe a dependent current source, and another resistor. But the idea here is you only have two nodes, one at the top, one at the bottom, and more importantly, you only have a single voltage variable, let's call it V sub x, the voltage difference between those two nodes. So here's the algorithm for solving single node pair circuits. The first thing is you want to define this voltage, this one voltage that's present in the circuit by some variable. Let's call it, for example, V sub x. And that is going to be the voltage across every element in that circuit because all the elements are in parallel. The next step then is you pick either node and you write a single KCL equation. So for example, if you pick this top node, you could sum up that current plus that current plus that current plus that current plus that current equals 0. So you're writing a single equation by applying KCL at either node. The key thing here is if you have a resistor, you could express its current by its voltage divided by the resistance. That's Ohm's law. So if you have a resistor here, if your voltage variable is Vx and the resistor's value is R sub k, its current we're going to express in terms of this voltage variable V sub x. Specifically, that current is V sub x over R sub k. The important thing to note here is the direction of the current arrow. If V sub x is defined with the plus on top and the minus on the bottom, this current has to be designated as going, once again, top to bottom. This does not mean that the actual current is going from top to bottom. That's going to depend upon the value of V sub x. At this point, V sub x is just a variable. We don't know that the top node is a higher voltage than the bottom node. That'll come out once we solve the problem. If you have a dependent source, we're going to see in an example, you treat it just like it was an independent source, except the controlling variable you want to write in terms of this voltage variable V sub x. Because what we want to end up with is a single equation where the only variable is V sub x. Step 3 then, once you write your KCL equation, you have one equation and one unknown. The one unknown is V sub x. You can solve for it. Once you solve for V sub x, if you need to find a current through a resistor, for example, you could use Ohm's law. If you want to find the power absorbed or delivered by a source, you can once again use the power equation, because once you know that voltage variable, you can find any voltage and any current in the circuit pretty easily. So let's illustrate this with one simple example. Here we have a single node pair circuit, two nodes, one on top, one on bottom. So we define a voltage variable, V sub x, and I will arbitrarily put the plus on the top and the minus on the bottom. This does not mean that the yellow node is a higher voltage than the pink node. We don't know that yet. We will not know until we solve the circuit. But you need to specify a polarity for that variable for when you write the equation. So that's the first step, is to define our voltage variable. In this case, we're going to call it V sub x. Second step now is we write a single KCL equation. And when we write that, V sub x is the only variable allowed. The idea here is we don't want to introduce new variables. We can choose either the yellow node or the pink node to write the KCL equation. I will use the top node, the yellow node. So basically I'm saying that this current plus that current plus that current plus that current has to equal 0. So let's sum all the currents leaving the yellow node. So if you look at this first branch, we have 6 amps entering that node, so we have negative 6 amps leaving that node, so negative 6. Second one, we have this current I1. We're not going to write it as I1 though. The only variables we want are Vx. So we want to write that current in terms of Vx. We know that when you have a resistor, the current through the resistor is the voltage across the resistor divided by the resistance. So the current going down is going from the plus to the minus terminal through the resistor, and so we can use Ohm's law, and it's plus Vx over 20. To look at the third branch, it's a dependent current source, it's 10I1. So it's going to be plus 10I1. We do not want to have the variable I1 in the equation though, so we write it as plus 10, And then we need to think, how can we express I1 in terms of Vx? Once again, we saw in the previous branch that I1 is just Vx over 20. So we write this as 10 times Vx over 20. Vx over 20 is our variable I1. Finally, our last branch, the current through the 5 ohm resistor is what? Vx over 5. We sum all those up and we get 0. Notice we have one equation and one unknown. So we can factor out the Vx. We get Vx times 1 over 20 plus 1 over 2 plus 1 over 5 equals 6. Solve for Vx. And you get Vx is equal to 8 volts. So by writing one equation and one unknown, making substitutions as needed and using Ohm's law as needed, we now know that the yellow node is 8 volts higher than the pink node. The fact it's a positive answer here basically means that our guess of the plus here and the minus here was correct. Had we defined Vx with the plus on the bottom and the minus on the top, our equation would have been different, and our final answer would have been Vx is equal to negative 8 volts, which once again just tells us that our initial guess would have been wrong. So at this point, we have now solved the circuit, but we have not answered the question. The question was not find Vx, the question was determine the power supplied by the 6 amp source. But now that we know Vx, we can now find that power. So if you think about the 6 amp source, for any circuit component, if you know the voltage across it and you know the current through it, you can find its power. We know the voltage across that source is 8 volts. We just solved for that. We also know that the current through that device is 6 amps going from bottom to top. How do we know that? Because it's a current source. So the absorbed power, using the power equation, is the voltage across the device times the current into the plus terminal. The current into the plus terminal is negative 6 amps. So the absorbed power, using the passive sign convention, is 8 times minus 6, or negative 48 watts. So basically this means this current source supplies 48 watts of power. We were not asked to find any other power or current, but if we were, it would be very easy to solve. For example, if we were asked to find the power absorbed by the 20 ohm resistor, that's just V squared over R. So 8 squared is 64 divided by 20 ohms, and you get that power. If you had to find a current, you could use Ohm's law. The current through the 5 ohm resistor is what? 8 volts divided by 5 ohms. So once you solve for this variable here, anything else you're asked to find in the circuit is trivial. Now let's look at single loop circuits. In a single loop circuit, every component is in series. So for example, you might have a voltage source, a resistor, maybe a dependent voltage source, a couple more resistors, another voltage source, etc. So in a single loop circuit, we have the following algorithm. The first thing we want to do is define a current variable I sub x. There's a single current throughout this whole circuit, so we define that current, and I typically like to make it a clockwise current variable, but it doesn't have to be. So you define your current variable. This does not mean that the actual current is going to be flowing clockwise necessarily. I sub x is a variable at this point. We don't know the direction of the current. But I pick a direction arbitrarily, I use that direction as I write our equation, and then when we solve for Ix, we find out at that point whether our initial guess of clockwise was correct or not. So once you define your variable, the second step is you write a single equation by applying KVL along the loop. Once again, you could go clockwise, you could go counterclockwise, you can sum voltage drops, you can sum voltage rises. I always like to go clockwise. I always like to sum voltage drops for reasons that we talked about earlier in this course. One thing to remember is when you have a resistor, let's say value R sub K, and let's say our current variable Ix is going in this direction through that resistor. The voltage across that resistor is then R sub K times Ix with the plus where? Because the current goes from higher voltage to lower, if I sub x is defined as left to right, the voltage, which is going to be R sub K times Ix, has to have that polarity. So once again, depending upon which way you define I sub x, that'll dictate which of these nodes you're calling the plus and which one you call the minus. Once again, until we know what I sub x is, we don't know that this is actually a higher voltage. It depends on whether Ix itself is a positive or negative number. And we'll see this in an example. In addition to dealing with the resistors, you deal with the dependent sources by writing the controlling variable in terms of Ix. And we'll see this in the example. When it's all said and done, you have a single equation in the variable Ix, and you solve that for Ix. Once you know that current, you can find any voltage across a resistor by using Ohm's law. If you want to find any power, you can use the power equation. Let's look at a simple example here. So we have a single loop circuit, and we're asked to find the power supplied by each source. So what we're going to do is, the first step, we're going to define our loop current variable Ix. I can define it clockwise, I can define it counterclockwise, it does not matter. I almost always define my current variables clockwise, however. Once again, this does not mean that this is necessarily going to be the direction of the final current. This is just the direction we're using when we write our equations in the next step. So the second step then is to write a single KVL equation in the variable Ix. Only variable that we want in this equation is Ix. So I can start at any point. I'm going to start on the bottom left here. And I like to sum voltage drops. Why do I like to do that? Because if I hit a minus sign first, I write it as a minus. If I hit the plus sign first, I write it as a plus. So I go through a 9-volt source. I hit the minus sign first, so it's minus 9 volts. Then I go through this 5 ohm resistor. It has a voltage across it, this new variable Vx, but we don't want to use that variable. The only variable we want is Ix. But we could use Ohm's law to determine that the voltage across the 5 ohm resistor is 5 times Ix. And where's the plus? Plus is at the coming from point of the current, the minus is at the going to point. This is how Ohm's law works. Once again, I'm not necessarily saying that the left point is at higher voltage than the right point, because that depends on whether Ix itself is a positive or negative number. But the way we define Ix, we have to put the plus on the left. So continuing, we get minus 9 plus 5 times Ix. Then we go through the 5-volt source. We hit the plus first, so we write plus 5. Then we go through a dependent source. Its value is 2Vx, and the plus is what we hit first, so we write plus 2. We don't want to write the variable Vx, though, because the only variable we want in this equation is Ix. So what we need to do is to write Vx in terms of Ix. Vx is the voltage across the 5 ohm resistor, and we already determined that the voltage across that resistor is also 5Ix. But notice the orientation of the Vx variable has a plus on the right, 5Ix has a plus on the left. So Vx is negative 5Ix. So we're going to rewrite Vx as negative 5Ix. Why is it that way? Because the way we defined Ix, the plus is on the left, and Vx is predefined with the plus on the right. Finally, we go through this 3 ohm resistor. Once again, its voltage is going to be 3 times Ix. But what's the orientation of the plus and the minus? Ix through that 3 ohm resistor is going from right to left, so the plus is here and the minus is there. So we get plus 3 times Ix is equal to 0. So notice we have an equation, and the only variable we have in the equation is Ix, which we can now solve for. Specifically, we get minus 2 times Ix is equal to 4, or Ix is equal to minus 2 amps. The fact that it is negative, what this means is that our initial guess of a clockwise current was wrong, and the physical current is counterclockwise. But that's fine, because it was just a variable when we defined it, and now we know the truth. So at this point, we've now solved the circuit by finding the current. We haven't answered the question, though, because the question was not what is Ix, the question is what is the power supplied by each source. So let's look at each source now. So for the 9-volt source, there's 9 volts across it. The current through that source is going from top to bottom. It is 2 amps going from top to bottom. The power absorbed is the voltage across it times the current into the plus terminal. So this source actually absorbs power. Most of the time sources supply power, but this one is actually absorbing power. For the 5-volt source, see what we have. Its voltage, of course, is 5 volts. For the 5-volt source, the current is going from bottom to top. We have 2 amps going that way. So the absorbed power is the voltage across the source times the current into the plus terminal. The current into the plus terminal is minus 2 amps. So we write that as minus 2 amps using the passive sign convention. Minus 10 watts. So the second source actually delivers power. And finally, the dependent source its value was 2Vx. But what is Vx? Vx was minus 5Ix. Since Ix is negative 2 amps, Vx is plus 10 volts, which means this dependent source is positive 20 volts. So this source has 20 volts across it, with the right terminal being a higher voltage than the left. The current through this source goes in this direction, 2 amps. So its absorbed power is its voltage times the current into the plus terminal, which was minus 2 amps, or minus 40 watts. So the 5-volt source and the dependent source both supply power. The 9-volt source absorbs power. By the way, we didn't ask for it here, but let's look at this. Let's look at the power absorbed by the 2 resistors. So the power absorbed by the 5 ohm resistor is what? We can solve it as I squared times R. The current is 2 amps. In fact, it's negative 2, doesn't matter because you have to square it. So 4 times 5, that absorbs 20 watts. And the power absorbed by the 3 ohm resistor is once again negative 2 squared. 4 times 3 is 12 watts. By the way, if you add up 20 plus 12 plus 18 plus negative 10 plus negative 40, what do you get? You get the sum of all the powers is equal to 0, which it has to, conservation of power. Now that we've discussed single loop circuits and single node pair circuits, we're going to take those concepts and apply them to the more complicated and more general nodal analysis and mesh analysis algorithms. So we're going to talk about nodal analysis first. Nodal analysis, we're basically going to have voltage variables, and we're going to use Kirchhoff's current law to solve. So it's going to be an extension of the single node pair circuit approach. Before we get into nodal analysis, a couple preliminaries we want to get out of the way. The first thing is that nodal analysis uses absolute node voltages. And if you remember, you can always indicate them without a polarity sign because it is always referenced to ground. So we're going to see in nodal analysis that we're going to have these variables that we're going to define at every node. It's just going to be a variable, VA, VB, VC, etc. But related to this, you must always indicate ground when using nodal analysis. The second preliminary is whenever you have any circuit element, the relative voltage across that element can always be written in terms of the absolute voltage at the 2 nodes. So for example, you have an element here. The voltage across it is, let's say, Vx. Vx you can always write as the voltage at one node minus the voltage at the other node. Which one you do as the plus and which one is the minus depends upon how the polarity of this variable is. So remember, Vx with the plus on the left and the minus on the right means the voltage at A with respect to B. We could also write it this way, VAB. But the bottom line, whenever you have a relative voltage variable, you can always write it in terms of the absolute voltage variable. By the way, if there was another variable Vy with the orientation like this, Vy would be Vb minus Va or VBA. But the bottom line is you can always write relative voltages in terms of absolute voltages, and in nodal analysis, we are always going to use absolute voltage variables. Third preliminary thing is dealing with resistors. So if you have a resistor, let's call this R. The current through the resistor, I sub x, is related to the voltage across it using Ohm's law. So I sub x is V sub x over R, Ohm's law. And notice once again the orientation. If I sub x is defined as going left to right, V sub x has the plus on the left and the minus on the right. But from the previous page, we saw that V sub x itself could be written as VA minus VB. This means that you can always write the current through a resistor by the difference between two absolute voltages. In this case, VA minus VB divided by the resistance. Another way to think about this, and I like to say this in my head as I do my equations, is the current through a resistor is the voltage at the coming from point minus the voltage at the going to point divided by the resistance. So once again, if I define my current variable in a certain direction, that current can be written in terms of the voltage at the coming from point minus the voltage at the going to point divided by the resistance. So I sub x would be VA minus VB over R, or we could use G, which is just 1 over R. Once again, I want to stress, we don't necessarily know when we're writing these equations whether the current in this example is actually going to go from left to right. It's a variable at this point. Whether Ix is positive or negative will depend upon the values for VA and VB. Let's now introduce the nodal analysis algorithm and do one example, and then we'll pick this up next class with more examples. But we're ready for the nodal analysis algorithm. With nodal analysis, we're going to see that there are two basic types of circuits. The first type of circuit is what we call grounded voltage sources only. What this is saying is that if there are voltage sources, and there don't have to be voltage sources in the circuit, but if there are voltage sources, they have to be either connected to ground or connected to another voltage source to ground. Current sources, if you have them, can be anywhere in the circuit. So for nodal analysis, we don't care where the current sources are, but if there are voltage sources and you want to use this algorithm, the voltage sources have to be either connected to ground or connected through a series of other voltage sources to ground. And we'll see this in an example. So the first thing you always do in nodal analysis is you need to determine ground. In some cases it's given, in some cases it's not. If it's given, you don't have to do this step. If it's not given, then what you want to do is assign ground so that you're grounding your voltage sources. Or, if there are no voltage sources, very often we just conveniently put ground on the bottom of the circuit. So it is important that you do define ground because you need that to solve circuits using nodal analysis. The second step is you look at every node in the circuit and determine whether the voltage at that node is known, in which case you write it down, or unknown, in which case you assign a variable. If you assign a variable, variable V1, V2, V3, etc. So you know the node voltage if there's a voltage source connected there. If there's not a voltage source connected to that node, then you do not know the voltage and you assign the variable V1, V2, V3, etc. Third step is for every node with an unknown voltage, you write a KCL equation. You sum the currents leaving that node. And when you write that equation, the only variables should be your V1, V2, V3, etc. So this step is similar to the one step in a single node pair circuit. Remember, in a single node pair circuit, you wrote a KCL equation and the only variable was V sub x. The only difference here is you might have more than one voltage variables. You might have V1, V2, V3. So rather than one equation and one unknown, you might have 4 equations and 4 unknowns, etc. The next step is we want to compile these equations together and then solve them. So for those of you who have had linear algebra already, you'll recognize this as a matrix equation. For those of you who haven't had a linear algebra course, it really doesn't matter. Basically what we're saying is we want to write our equations as something times our v1 variable plus something times v2 plus something times v3 all the way up to our last voltage variable, V sub n, equals, and there's going to be a number on the right. So if we have a total of 5 variables, we're going to have a total of 5 equations. So we're going to have 5 equations and 5 unknowns, 3 equations and 3 unknowns, 2 equations and 2 unknowns, etc. So once you set up your system of equations, you want to solve it for the unknown voltages. Once again, if you've had a linear algebra course, you know simple ways to solve equations. If you haven't, you basically need to do some substitutions to try to solve for the variables. At this point, we have now determined the voltage at every node in the circuit. So we've solved the circuit, but we haven't necessarily answered the question. That depends upon what the question is asking. So the last step then is, if necessary, we can now use Ohm's law if we want to find the current through the resistor, for example, or if we want to find the power absorbed or supplied by one of the devices, we can use the power equation. And finally, and this is an important point here, we'll see this in some examples, if you need to find the current through a voltage source, you can apply KCL to determine the current through that voltage source. An important point is the only time you ever write a KCL equation for a node attached to a voltage source is to find the current in that voltage source, and you do that after you find all of the node voltage variables. So let me repeat this because it's important. The only time that you ever write a KCL equation for a node attached to a voltage source in this algorithm is if you want to find the current in that voltage source, and you do this only after all node voltages have been determined already. So let's do one simple example illustrating this algorithm. In this problem, we're asked to use nodal analysis to find the power supplied by each of the sources. So the first step you need to do is determine whether ground has been defined. Ground has not been defined, so we need to define ground. So let's look at where different nodes are. There's a node here, there's a node here, there's a node here, and there's a node here. So this circuit has 4 nodes. So we have 4 potential places we can put ground, but because we're using this algorithm for type 1 circuits, the voltage source, this 10-volt source, has to be grounded. So we cannot put ground on the yellow node because that would make this 10-volt source a floating source, as we call it. We cannot put ground on the green node for the same reason. We could put ground here, but that's not very logical. Instead, the logical place to put ground would be on the bottom of the circuit. So we need to establish what we're calling our 0-volt reference point. Basically, we're establishing our C level for this circuit. That's the first step. Next step is you look at every node and determine whether you know the voltage at that node. So for the yellow node, is there a voltage source attached to that? No. So we do not know its voltage, so we're going to assign a variable. I'm going to call it V sub 1. The blue node, do we know the voltage at that point? The answer is yes. Because the blue node is attached to a voltage source that is attached to ground, we know that this blue node is 10 volts higher than the pink node. Since the pink node is at ground, we know the voltage here is 10 volts, so we write that down. Green node, do we know its voltage? Once again, it is not attached to a voltage source. We do not know it, so we're going to write a variable V2. So at this point, we've now defined our voltage variables. Now we know that we're going to have to write 2 KCL equations in 2 variables, V1 and V2. The only variables we want in these equations are V1 and V2. So the next step then is to write the KCL equations for both the yellow node and the green node. So for the yellow node, we know that this current plus this current plus this current is equal to 0. So for the V1 node, the KCL equation is what? The current going down, we have 1 amp going up, so the current going down is minus 1 amp. Current going up is a current through the 2 ohm resistor. Remember, the current through a resistor is the voltage at the coming from point minus the voltage at the going to point divided by the resistance. So the current through the 2 ohm resistor is the voltage at the coming from point, V1, minus the voltage at the going to point, V2, divided by 2 ohms. So we get plus V1 minus V2 over 2 ohms. For the 4 ohm resistor, the current is the voltage at the coming from point, V1, minus the voltage at the going to point, which is known, 10 volts divided by 4. So we get plus V1 minus 10 over 4 is equal to 0. Basically, the current going down plus the current going up plus the current going to the right is equal to 0. Notice the only variables in this equation are V1 and V2. We can then re-express this as 3V1 minus 2V2 is equal to 14. We do the same thing for the V2 node. That current plus that current plus that current is equal to 0. Current going down, current through the resistor is the voltage at the coming from point, V2, minus the voltage at the going to point, in this case ground, divided by the resistance. So we get V2 minus 0 over 2.5. Current going to the left is V2 minus 10 over 10. Current going up is V2 minus V1 over 2. Sum those, it equals 0. One thing to note here, notice that in the first KCL equation we had V1 minus V2 over 2. In the second equation we have V2 minus V1 over 2. That's because both KCL equations have the same current, the current through this branch here. The reason they're opposite in sign, though, is because we're always summing the current leaving that node. So for the V1 node, we're doing the current going left to right, V1 minus V2 over 2. For the V2 node, we're doing the current going right to left, so it's V2 minus V1 over 2. One other thing I want to point out here is if you use the algorithm where you're always summing the currents leaving the node, which is what I like to do, when we're doing the V2 KCL equation, notice the expressions are V2 minus something, V2 minus something, V2 minus something. When we're writing the V1 node KCL, notice it's V1 minus something, V1 minus something. So that's going to be the structure, is if you're doing KCL and doing the currents leaving the node, it's always going to be that voltage minus the voltage on the other side of the resistor. So it's going to be a V1 minus, V1 minus, V1 minus. In the other case, it's going to be a V2 minus, V2 minus, V2 minus. If you sum the currents entering the node, guess what? You do not have that nice structure. That is one of the reasons why I like to sum the currents leaving the node. Anyway, you can simplify this to get the structure of minus 5V1 plus 10V2 is equal to 10 volts. So now we would set this up as a matrix equation. So for those of you who have had linear algebra, you'll recognize this structure. Whether or not you've had a linear algebra course and know how to solve this matrix problem, you certainly have had in an algebra class, you've learned how to solve these simultaneously. So solving two equations and two unknowns, whether you do it using matrices or other methods, is really up to you. But basically you solve this and you get our variable V1 is equal to 8 volts and our variable V2 is equal to 5 volts. So at this point we have solved the circuit. We now know the voltage at every node. V1 was 8 volts. V2 is 5 volts. And of course this blue node, we already knew it was 10 volts, and of course the pink node we know is ground. So at this point we solved the circuit, but we have not answered the question, because the question wasn't find the voltage at every node. The question was find the power supplied by each of the sources. But now that we know these voltages, we could use this information to answer this question. So if you look at the 1 amp source, if you look back to the previous page, its bottom node is connected to ground, the top node is at 8 volts. So we know the voltage across this source is 8 volts. So the absorbed power is what? The voltage across the source times the current into the plus terminal. Current going in this direction is minus 1 amp. And so we get 8 volts times minus 1 amp, or minus 8 watts. So this thing supplies 8 watts of power. For the 10 volt source, we need to find its current. And this is where we're going to do this last step here. You don't always have to do this last step. It depends upon what you're asked in the problem. But here, to find the power supplied or absorbed by the 10 volt source, we need to find its current. So what we're going to do now is a KCL equation right here. Notice we did not do KCL there before. We did KCL at this node, and we did KCL at this node. We did not do KCL in this middle node. The only time you ever do a KCL equation on a node connected to a voltage source is to find the current into that source, and you do that only after you know all the voltages in the circuit. At this point, we know all the voltages in the circuit, so now and only now we could write a KCL equation at that blue node. So for the 10 volt source, let's redraw that part of the circuit. So we know we have a 4 ohm resistor here. We had a 10 ohm resistor here. We had our 10 volt source. We had ground here. There was other stuff in the circuit too. We really don't care about that. We're concerned about this node here. We also know that the voltage at this point is 8 volts. We determined that already. We know the voltage at this point is 5 volts. And of course, we know the voltage at this point is 10 volts. So now and only now we can do KCL at this blue node. Basically, that current plus that current plus that current is equal to 0. Let's define the current coming out of the source as IS. That is the current being generated by this source. So now let's solve for IS by doing KCL at that blue node. So from KCL, current to the left, the current through the 4 ohm resistor, is 10 minus 8 over 4. So notice we're using Ohm's law like we did before, but before when we found the current through this 4 ohm resistor, we did not know V1, we left it as a variable. Now we know the value, so we plug it in. So we get 10 minus 8 over 4, plus the current to the right is 10 minus 5 over 10, minus IS is equal to 0. So we can now solve for IS, and we see that IS is equal to what? 1/2 plus 1/2, or 1 amp. Now that we know that, we can now find the power associated with this 10 volt source. The absorbed power is what? The voltage across the source times the current into the plus terminal, which was minus 1 amp. So it absorbs minus 10 watts, or supplies positive 10 watts of power. So at this point, we've done a fairly simple example using the nodal analysis algorithm. We will pick this up next class to do more examples. We'll look at dependent sources, and we'll look at what happens when you have what's called a floating voltage source. That is a voltage source that is not connected to ground, and we'll see that that introduces some complications, and we need to change our algorithm a little bit to solve those types of circuits. Anyway, we'll see that next time, so have a good day.